Hello everyone and welcome back. My name is Mr. Koval and today I'm going to be going over constant pressure calorimetry where we're going to measure the delta H of a reaction. This is going to also involve something called coffee cup calorimeter. And so when we're talking about a coffee cup calorimeter, basically that's what it is. We got two styrofoam cups. One is going to be nested in the other. And so this is typically the kind of calorimeter that you're going to mix two solutions together. So like maybe I have one beaker has a base and the other beaker has an acid, and I measure the temperatures of the acid and base before I mix them together, and then I mix them together in the coffee cup calorimeter. Or better yet, I'll have maybe the acid in the coffee cup calorimeter already, and then when I'm ready I put the acid or the base in and I mix it up in the coffee cup calorimeter, and then I'll put a top on it, and then there's a mixer, there's a stirrer as well as a thermometer, so it'll look something like like this. So here's my coffee cup here. And then nested inside that will be a second coffee cup. And so I'll have a top on top, a lid, and then there'll be a stir bar, so some sort of maybe glass stir bar, and then I'll also have a thermometer measuring the temperature before and after mixing. And so I'll have my solution inside. And so here we'll have the reaction occurring inside of a solution. And so with the coffee cup calorimeter, the coffee cup calorimeter itself is not going to absorb any of the heat, and we'll assume that all of the heat was transferred from the reaction to the solution itself. So in this case, the solution is going to be the surroundings, and the reaction itself is going to be the system. And that's all. So that's why we're using a coffee cup calorimeter to limit the transfer of heat from the reaction and only have it transferred to the solution or from the solution to the reaction. So in that case, we would have to know what the the specific heat of the solution is. That would have to be given to us, because if the solution is going to absorb or lose heat, we would have to be able to figure out the amount of heat that is absorbed or is given off. And again, the specific heat of the solution is going to have the units joules per gram degrees Celsius. And so again, the formula, in order to get the joules, the formula would have to be you multiply by a mass and a temperature change. So the Q, the heat gained or lost by the solution, is going to be equal to the mass of the solution multiplied by the specific heat of the solution, and then multiplied by the change in temperature. So delta T of the solution. So, so this would represent any heat or that is lost or gained by the solution during the reaction. And so, since in the coffee cup calorimeter the only things that are involved is the solution and the reaction, then the solution, the Q of the solution, is going to be equal to negative Q of the reaction. Okay? So because they're equal and opposite. So whatever the solution gains, the reaction is lost. Whatever the solution loses, that is gained by the reaction. And so we saw before that under constant pressure, like so if this is, in the open under atmospheric pressure, we're mixing two solutions together, so there's really no volume change as far as gases and stuff like that being produced. So this is going to be under constant pressure, and so therefore the work being done is 0. So remember the equation, delta E is equal to delta H plus the work, right? So P delta V, but then this is work, but then of course we're going to replace that with also negative work. So this is going to be gotten rid of. And so then what happens is that this delta Q of the reaction ends up being equal to delta H of the reaction, the enthalpy of the reaction. So, or negative enthalpy of the reaction. So here, we can set the equation. So the enthalpy of the reaction, or the negative enthalpy of this reaction, is going to be equal to the mass of the solution times the specific heat of the solution times delta T of the solution. So they're going to be equal and opposite. But remember, in a lot of problems, in this problem, it's like you only got two things to worry about. You've got the reaction, the enthalpy of the reaction, the heat of the reaction, and then you've got the solution itself. But you could also have, you can have a block of some metal thrown in there. You can have ice dissolving or melting. You could have a reaction going on at the same time, and so on. So again, the best way is to set everything equal to 0, since no energy is lost, created, or destroyed in the universe. So everything is going to be equal to 0, and then you've got your Q1 plus your Q2 plus your Q3 plus, and then whatever other heat absorptions or heat gains or losses are being involved. So you're gonna, what's being absorbing the heat, what's losing the heat. So again, this could be, if you've got this reaction going on in solution, then this Q1, you could say, okay, that's the Q of the solution. And then that would be determined by this equation here, right? So you'd have to determine that by mass of the solution times the specific heat of the solution multiplied by some change in temperature. Okay, and then maybe this Q2, if you've got a reaction going on, maybe that Q is the delta H of the reaction, right? So delta H of the reaction, a lot of times that's going to be kilojoules per mole, right? So you've got a certain number of kilojoules per mole. Well, maybe you're given a certain gram amount of reactant that's reacting, right? So you're going to need to figure out the total Q value that comes from the reaction based upon the amount of reactant or the amount of product that you're given, right? And if it's kilojoules per mole, then you're going to need to convert to moles. And then, of course, you would multiply. So Q in this case, Q would equal this Q2, the Q, we'll call it Q of reaction, or delta H of the reaction. So the Q of the reaction would equal the delta H multiplied by N for number of moles. So that way you would get kilojoules. Okay, this is probably going to be in joules. Maybe this Q here, maybe that has to do with the melting of ice, right? So you're going to need to know the amount of heat absorbed by the ice that's going to melt the ice. So there you're going to need, this is the Q, this will be Q of water. And again, you're going to need to know the mass of the water. You're going to need to know the specific heat of ice, right? Because liquid water, ice, solid water, gaseous water, they all have different specific heats. So this would be the specific heat of ice multiplied by, again, a temperature change. So each time you have a different Q value that's involved in the mixture or in the problem, you need to figure out which Q is which and then determine what formula is going to give you that Q value. And then you just plug that into the equation here, all set up to equal 0. And then at that point, the problem is asking you for some missing part. Maybe it's a mass of the solution. Maybe it's the final temperature, right? So at this point, you should be able to solve the equation because you'll only have one unknown depending on what the problem is asking for. Another thing to watch out for is a lot of times you'll need the mass of the solution for this part of the equation, but they'll give you a density. Or you're going to want to assume the density is equal to the density of water if they don't give you a density. So they'll have to give you a specific heat of the solution if they don't give you the specific heat, or if they tell you the specific heat of this solution is assumed to be equal to that of water, then you can assume that the density is equal to water as well. It just depends on what they give you in the problem and what it's safe to assume if they don't give you that. So that I hope is clear, and I hope this was helpful. Let me know what you think in the comment sections. Let me know if you have any questions or if you want me to go over anything else. If you like this video, share this video, hit the notification bell if you want to get more, if you want to be notified by any videos I put out. Hit the like or subscribe to the channel, and again, put a comment in the comment section. Thanks for joining me, and I'll see you next time.